All right, today we're going to talk about the 10 papers that basically built the entire world of modern AI as we know it.
Neural networks have actually been around since the 1940s. So, how did AI get so smart, so fast, seemingly overnight? Well, the answer lies in a series of absolutely incredible breakthroughs that all happened in just the last few years.
Okay, let's dive in. This timeline right here, this is our roadmap. We're going to start back in 2017 with the game-changing transformer, and then just race through to the big ideas of today. Everything from making models smaller and smarter to actually connecting them to the real world. This is the story of how we got here. So our story begins with what is probably the single biggest shift in modern AI history, the transformer revolution. This was truly the spark that changed everything. Before 2017, AI models were kind of like slow, methodical readers. They processed text one word at a time. This was incredibly slow, and it made it really hard for them to connect ideas in long documents. Then, bam, the transformer comes along and completely changes the game. It was designed to look at all the words in a sentence at once, which meant we could finally use GPUs for massive parallel training. The result? Way faster training and a much, much deeper grasp of context. The magic ingredient that made all this possible is called self-attention. It's a really clever way for the model to weigh the importance of every single word in relation to all the others, and do it all at the same time. This is the key that unlocked both that parallel processing power and that deep contextual understanding. So with this new architecture, models became incredibly powerful. But raw power isn't the same as being useful. The next phase was all about unlocking their true capabilities and turning them from these raw engines into the helpful assistants that we see today. The next big leap forward came in 2020 with the GPT-3 paper, and it revealed something that was almost an accident. If you just make a transformer model big enough, like really big, it starts to develop entirely new abilities out of nowhere. This concept of emergence, where just scale itself unlocks new skills, was a massive surprise to the entire field. And the key new ability was something called in-context learning. This meant you no longer needed to completely retrain a model for every single new task. You could just give it instructions and a few examples, what we now call shots in a prompt, and the model could just figure out what to do. This completely changed how developers built AI systems. But of course, there was a catch. These huge, powerful models could also be pretty unhelpful, spout nonsense, or even be toxic. This created a brand new critical problem for the field to solve: alignment. How do you make sure the AI is actually trying to do what you want it to do? The answer came in 2022 with the InstructGPT paper, which introduced a powerful three-step process you might know as RLHF. First, they fine-tuned the model on examples of good, helpful responses. Second, they trained a whole separate reward model to basically act as a judge, scoring answers based on human preferences. And finally, they used reinforcement learning to tweak the main model so it would produce answers that this reward model judge would give a high score to. This whole process was key to making models much more helpful and reliable. Okay, so now we have models that are both powerful and aligned. Great. But how do we make them truly useful in the real world? The next step was all about connecting them to our data and our tools. One of the best ways to make a model useful is to fine-tune it on your specific data. But training all the parameters of a massive model is incredibly expensive. So the question became, is there a more efficient way to do this? And the answer was a resounding yes. The 2021 LoRa paper introduced a radically more efficient technique. Instead of training 100% of a model's parameters, LoRa inserts these tiny adapter layers and only trains those. We're talking less than 0.01% of the total. That's a 10,000-fold reduction in trainable parameters, making custom fine-tuning accessible to almost everybody. Another huge problem is that models only know what they were trained on, which can be years out of date. The solution, proposed way back in 2020, is Retrieval Augmented Generation, or RAG. Before answering, the model retrieves fresh, relevant information from an external source, like your company's database or the live web, and then uses that to form its response. This is how you fight both stale knowledge and hallucinations. But what if we want models to do things, not just answer questions? Well, that's where agents come in. A 2023 survey paper laid out this simple but powerful loop. The LMM acts as the brain, making a plan. It uses perception to gather information from tools or files. Then it takes an action, like calling an API. It sees the result and repeats the loop.
This is how AI starts to interact with the world.
All of these incredible capabilities come with the cost. Model size. They can be enormous and expensive to run. This brings us to the next great challenge, the quest for efficiency, making AI smaller, faster, and cheaper.
One very clever idea is the mixture of experts, or MOE. Instead of one giant network, you have many smaller expert networks. For any given task, a router activates only the one or two most relevant experts. This means you can build a model with trillions of parameters, but it's still fast and cheap to run because you're only using a tiny fraction of it at any one time. Another approach is to simply shrink the model. Knowledge distillation is a technique where you use a large, powerful teacher model to train a much smaller student model. The goal is just to transfer all that knowledge into a more compact package. Just how effective can this be? Well, the 2019 Distelbiert paper showed you could create a model that was 40% smaller and 60% faster than its teacher while still keeping 97% of its language understanding. This is the kind of efficiency that makes it possible to run powerful AI on edge devices like your phone.
And finally, there's quantization. Think of it as just reducing the precision of the numbers, the weights, inside the model. By using simpler numbers, like 8-bit integers instead of 32-bit floats, you can drastically cut down the model's memory footprint and speed up calculations, often with almost no loss in performance. The LLM.int8 paper made this practical for even the largest models. So we've covered architecture, capabilities, and efficiency. The final piece of the puzzle is about creating a common language for AI to standardize how it interacts with the digital world. And this is where the Model Context Protocol, or MCP, comes in. Announced by Anthropic in 2024, it's an open standard designed to be a universal plug for AI. Instead of building custom integrations for every single tool and API, MCP creates a standard way for any model to connect to any tool. It's a vision for a much more interoperable AI ecosystem. So from the transformers architecture to the efficiency of quantization and the interoperability of MCP, these papers really are the foundational building blocks. They aren't just isolated ideas, they build on each other to create the powerful AI we have today. Each one of these papers solved a major problem and created the foundation for the next wave of innovation. Which leaves us with one final thought. What breakthrough happening right now will be the foundation for tomorrow's AI?